Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another topic. The topic of today is, let me use this color, components of vectors. So components of vectors we have to discuss in today's lecture. So let us start. You have done this idea in your class 11th, but I am repeating it here so that you can connect to the syllabus of your second semester. So in last lecture, we discussed the properties of vectors. We defined vector addition with graphical method, but in 3 dimensions, that graphical method of adding vectors is not very useful. Often it is inconvenient even for the 2-dimensional case. Another way of adding vectors is the analytical method, involving the resolution of a vector into components with respect to a particular coordinate system. Consider this figure to understand this. So let me draw the figure. Let me use another color. Let me complete the figure, then I will explain it. Let me name it figure 1. And this be the part A of the figure. I will draw another part. So in this figure 1A, we have a vector A whose tail has been placed at the origin of a rectangular coordinate system. Now if we draw perpendicular lines from the head of vector A to the axis, this line and this line, the quantities this AX and AY so formed are called Cartesian components of vector A. So this AX and AY are called Cartesian components of vector A, right? We're drawing perpendiculars from the tip of the vector on the x-axis, then the length from the tail of the vector, that is origin, to the foot of the perpendicular on y-axis is AY, and from the tail of vector A, that is origin O, to the foot of perpendicular on x-axis is AX. So these two quantities, AX and AY, are called Cartesian components of vector A. And this process is called resolution or resolving a vector into its components. Right? Now you have to understand that vector A is completely and uniquely specified by these components. That means given AX and AY, we could immediately reconstruct the vector A. Another thing, the components of a vector can be positive, negative, or zero. In this case, X and AY both are positive. But if I draw another figure, part B of the figure like this, this be my X, this be my Y. I construct another vector using this color. This is my vector B. Now I draw the perpendiculars on the axis. Now this length is Bx. This length is By. This is my angle phi. This is part B of the figure. So I'm saying that the components of the vector can be positive, negative, or zero. Now in figure 1a, vector A has components x and ay. They are both positive. In figure 1b, a vector B has bx negative and by positive, right? So they can be positive or negative depending on the vector, how it is oriented, whether it lies in first quadrant, second quadrant, third quadrant, or fourth quadrant. Accordingly, you have to see the sign of its rectangular components. Now, the components AX and AY in figure 1A are readily found from, you can see from this figure 1A, AX is just A cos phi and AY is A sin phi. A is the length of this vector. So this length AX can be written as A times cos phi, and this length AY, which is same as this length, can be written as A sin phi. Let me name this equation as 1. So from 1, knowing the length and the angle of the vector, that is magnitude and direction of the vector, you can find from 1 its rectangular components. But you have to understand this, that this phi, this is the convention, phi is the angle. Phi is the angle that the vector A makes with the positive x-axis measured, this is important, counterclockwise from this axis. That means this angle, when we refer to the angle made by the vector, we talk of this angle, phi. That vector makes with positive x-axis measure counterclockwise, that is anti-clockwise fashion from this axis. Now, as shown in figure 1, the algebraic signs of the components of the vector depend on the quadrant in which the angle phi lies. For example, when phi is between 90 degree and 180 degree, as in figure 1b, you can see the vector always has a negative x component and a positive y component. Another important thing, the components of a vector behave like scalar quantities. The components of a vector behave like scalar quantities. Because in any particular coordinate system, only a number with an algebraic sign is needed to specify them. So remember this. Once a vector is resolved into its components, the components themselves can be used to specify the vector. Now, instead of two numbers, that is A, which represents the magnitude of the vector, and phi, another number, which represents the direction of the vector related to the x-axis, we now have the two numbers ax and ay, right? Now we can pass back and forth between the description of a vector in terms of its components ax and ay, and the equivalent description in terms of magnitude and direction, that is a and phi. To obtain a and phi from x and ay, we see from figure 1a, we can write, I can use here Pythagoras Theorem. This is ay, this is also ay. So I can use Pythagoras Theorem and express the magnitude in terms of x and ay. So from figure 1a, I can write a, magnitude of the vector a, as square root of ax square plus ay square, and I can write tan phi as ay by ax. You can see tan phi is ay by ax, and a square is x square plus ay square. So a is the square root. So let me name this equation second. These equations are second. So you can see in second, knowing x and ay, you can find a and phi. That's magnitude and direction of the vector. And in one, knowing magnitude and direction a and phi, you can find components. So these are two equivalent descriptions of a vector, whether you specify it in terms of components or in terms of magnitude and direction. Two numbers are required to specify it in two dimensions. We are talking in two dimensions. Now the quadrant in which phi lies is determined from the signs of x and ay. Now in three dimensions, the process works similarly. Just draw perpendicular lines from the tip of the vector to the three coordinate axes x, y, and z. Then we have three components, ax, ay, and AZ, right? Now, in the last lecture, we defined unit vectors. We said a unit vector is a vector with magnitude 1 and is dimensionless. Now we define 3 spatial unit vectors: I cap, j cap, and k cap. I cap is a unit vector along positive x-axis. By definition, j cap is a unit vector along positive y-axis, and k cap is a unit vector along positive z-axis. So in diagram, I can show them. If this is my x-axis, this is my y, and this is my z direction, then I cap is along positive x direction. Let me use another color. J cap is along positive y direction, and k cap is unit vector along positive z direction. So I cap is along positive x, j cap is along positive y, and k cap is along positive z direction. What we do, we can express a vector in terms of its components in unit vector notation. We have a notation. I can write A as AXI cap plus AY j cap. Now in 3 dimensions, we have 3 components. We have AZ as well. Then I can write A as AXI cap plus AY j cap plus AZ k cap. This is called unit vector notation of a vector. Unit vector notation of a vector, right? So once a vector is determined fully, you can express it in unit vector notation. And unit vector notation means that vector is completely known. If we know its all the components, then we can express it in unit vector notation. There's another thing. We know in graphical method how we add vectors. We can use triangle law, we can use parallelogram law of vector addition. The question is how we add vectors using component method. I will write adding vectors component method is also called analytical method of adding vectors. So let us discuss this. First, you need to understand the idea of equality. When we say 2 vectors are equal, we say their magnitudes are equal and they are similarly directed. Now, in component interpretation, equality means all the components of a vector of vectors are equal. If I have vector A and vector B, they are equal when all their components are equal, corresponding components. That means when AX is equal to BX, AY is equal to BY, if the vectors exist in 3 dimensions, then AZ is equal to BZ. So equality means in this component method that all the components are equal. What about negative of a vector? In graphical method, we say if this is vector A, then minus A is a vector having same magnitude but opposite direction. In component interpretation, minus A means that minus A is a vector which has negative times all components negative times the component of A. That means if components of A are AX, AY, AZ, components of minus A are minus AX, minus AY, minus AZ, right? Another thing is zero vector. Zero vector means a vector which has all the three components as zero, right? So let us move now. Now, how we add vectors using component method. So for example, if we have two vectors, vector A, we are talking in 2 dimensions, and vector B, and we have the vectors are in 2 dimensions, and from triangle law, this S is the sum vector. So let the unit vector notation of A be AX I cap, we are talking in 2 dimensions, AY J cap, and the unit vector notation of BB BX I cap plus BY J cap. Then the resultant or sum vector S, which is A plus B vector, is what? It will have some unit vector notation Sx I cap plus Sy J cap. When you put the unit vector notation of A, which is Ax I cap plus Ay J cap, then unit vector notation of B, Bx I cap plus By J cap. You can factor out I cap, you can write it X plus Bx times I cap plus Ay plus By times J cap. So what is the conclusion? Conclusion is if you check your left hand side and right hand side, conclusion is Sx is equal to Ax plus Bx, and Sy, y component of some vector, is Ay plus By. You can see from this also that two vectors are equal to each other only if their corresponding components are equal. So Sx is Ax plus Bx, Sy is Ay plus By. Now, if you are interested in finding the magnitude of the resultant vector, you know that will be square root of Sx square plus Sy square. So you can write it in terms of the components of A and B. You can write it square root of Ax plus B, you substitute for Sx plus Ay plus By, then square. So you can see, knowing components of A and B, you can find the length of resultant S from this equation. You can find the direction of S also. You know tan phi is Sy by Sx. So Sx you replace by Ay plus By, then you divide by Sx, which is Ax plus Bx, right? So knowing components of A and B, you can find the direction of the resultant and you can find its magnitude also. So you can see how we add vectors using component method. You simply add the corresponding components. For example, if if A is given as minus 3i plus 6j and B is given as 2i minus j, then what is A plus B? X component of A plus B, that is what is attached with I cap, coefficient of I cap is sum of X components of A and B. X component of A is minus 3, X component of B is 2, minus 3 plus 2 is minus 1, it's minus I cap. Then to find what is the Y component of some vector, that is what is attached with J, you have to add the Y components of A and B. Y component of A is plus 6, B is minus 1, plus 6 minus 1 is plus 5. So it's plus 5 J cap, this A plus B vector. Simple. You added minus 3 with 2, you got minus 1. So it's minus I cap. You added 6 with minus 1. 6 minus 1 is 5. So you got plus 5 as the Y component of A plus B. So it's easy. You don't need to construct the vector graphically to the scale and find your results. In analytical method or component method, you have to just make the calculations as you do with numbers, right? There's another idea which we have to discuss. I think I will keep that for next lecture. I will give you some home assignment. Let me give you the question. So the question goes like this. Let me write it in red. Given two vectors, A equal to 4i cap minus 3j cap and B equal to 6i cap plus 8j cap. Find the magnitudes and directions with the positive x-axis of part A is vector A, part B is vector B, part C is vector A plus B, part D is vector B minus A, part E is vector A minus B. Let me check the question. Given two vectors A equal to 4i minus 3j and B equal to 6i plus 8j, find the magnitudes and directions with the positive x-axis of vector A, part A, vector B, vector A plus B, vector B minus A is light. I will change color here. B minus A, and E part is A minus B. So this is all for today. Go through all the lectures, do this homework, don't waste your time. And don't forget to like, share, and subscribe my channel. You can comment in the comment box. Thank you. God bless you. Assalamu alaikum.